I'm going to do a little short section right here, and it really deserves a lot more than attention than I'm giving it. But this is the de Broglie matter wave, and yes, I am pronouncing it correctly. I have conversations with other faculty and students who argue it's pronounced de Broglie, but no, it's de Broglie. And the de Broglie matter wave is really going from where we're looking at light as having a dual particle wave nature, and now we're going to say that matter has this dual nature to it. Now, basically, in 1924, we discussed that Compton had explained the Compton scattering, which established that, in fact, that X-rays had a wave and a particle nature to them. And this led de Broglie to think that, well, maybe since light could have a particle nature, why can't matter, which has a particle nature, also have a wave nature to it? So we look at our equation for relativity, and we're going to discover that, yes, in fact, that the wavelength is equal to Planck's constant divided by the momentum. This is something that we saw for light. However, if we replace the momentum, which for light is different, it's E over C, with the momentum for a particle with mass, we get this expression here, where the wavelength is equal to Planck's constant divided by mv. And again, we get this basically by taking our energy momentum equation. Okay, we're going to derive for light. We did derive this for light. We saw the relationship between energy, momentum, and the speed of light. We knew that the energy is equal to Planck's constant times the frequency. Now, if we merge these two ideas together and we say, okay, momentum is energy divided by the speed of light. Energy is the Planck's constant times the frequency of light. Can't we just also do that for the electron or for any other thing with matter? So essentially, de Broglie was taking an old idea and reappropriating it for particles with mass. And this had very important consequences. Here we see the de Broglie wavelength once again. We can even assign a frequency according to the energy and Planck's constant. Again, we know that wavelength is inversely proportional to frequency. So obviously, if we take the fact that the velocity is equal to lambda f, we can replace lambda and velocity with frequency and get this expression here. Now, the de Broglie wavelength doesn't work so great for large objects. Anything with mass does have a wavelength associated with it. So let's take a softball. I'm going to take a softball traveling at 30 meters per second, okay? Slow pitch. I think that's slow pitch. I don't know, 65 miles per hour, I guess, might be a little bit faster pitch. But in any case, if I calculate my de Broglie wavelength for a very common macroscopic object traveling, the very small size of Planck's constant will actually make an extremely small wavelength. So lambda is equal to h over p. The momentum is mass times velocity. This thing isn't traveling at the speed of light, so we don't have to do any corrections for relativity. But the wavelength we get is absurd. It's 1.23 times 10 to the minus 34 meters, which is really too small to be meaningful. It's really, in terms of the softball itself, that wavelength doesn't really mean anything. Even the nucleus is 10 to the minus 15 meters across. So this is, 19 orders of magnitude smaller than that. So this is nice. This is what we want. We want the wavelength properties to disappear as we go to the macroscopic scale, so everything behaves classically in that classical approximation that we're very used to. We don't want the wavelength to show up until we go to the very, very small realm. So let's try this for a subatomic particle now. Okay, we'll try this for an electron. Electron, 9.11 times 10 to the minus 31 kilograms. We're going to accelerate it to a moderate velocity, 1.5 times 10 to the 6 meters per second. Okay, so we're okay. We're not near any relativistic speed. You know, we're well below even 1% of the speed of light. But what would our wavelength be for this particular case? It's going to be small. Planck's constant divided by mv. Here's our mass, which helps offset this very small Planck's number. And here's our velocity right here. And we get a wavelength of 0.85 nanometers. So that's about 1,000 times smaller than blue light, but we're now on a wavelength that we can actually observe that. We could actually use these electrons. We'll see this later on. If we could focus them, we could use them to make an electron microscope. We'll actually see that this wavelength right here is actually quite large for some of the microscopes that operate. But again, clearly smaller than the wavelength of light, but it's still meaningful as far as the electron goes. Proton, as we make our mass much larger for the same velocity, as we might expect, the wavelength is going to get smaller. Just like when we had the softball, that mass was tremendous. Therefore, we still ended up with a small wavelength. But the wavelength is getting smaller as the mass is getting larger, and obviously we expect that the proton, having more than 1,000 times the mass of the electron, is going to have a wavelength that's more than 1,000 times smaller. So that is our proton. What if we make an electron relativistic? Well, look at this equation. As we make V larger and larger, the wavelength is going to get smaller and smaller. So thinking forward to the electron microscope, if we wanted higher and higher resolution, we would give those electrons more energy. The problem that we faced is that as the electrons go faster and faster, they also carry with them more energy. So you can actually end up damaging samples. And there's a limit to how much you can really observe. There's a limit to how energetic we can make these electrons before we destroy the sample, before making anything meaningful. So that's something to keep in mind, that we are showering the sample that we're trying to look at with very, very energetic particles when we get up to relativistic speeds. So relativistic speed, let's send the electron up to a speed where we might find it in an electron microscope. 2/3 the speed of light gives us a Lorentz factor of 1.34. We see now that the wavelength is quite small. We're now down into the picometer range. Just to give you an idea, when we think about visible light is about half a micron, okay, or is measured in the hundreds of nanometers. So a nanometer is 1/1000th of a micron. A picometer is 1/1000th of a nanometer. So what this represents here is very, very small wavelengths when we do compare them to the wavelength of light, really on the order of wavelengths that we would see for, very hard X-rays and gamma rays. Now, de Broglie extended his wave theory of matter. This is the really beautiful step that he took right here, and he wanted to find out why, or I guess he wanted to explain why only certain orbital energies were allowed. Of course, Bohr's theory of the hydrogen atom had that only certain quantized amounts of angular momentum are permitted. And this is the condition that we see right here, that LE is equal to N times H bar, and that when n equals 1, we have the lowest state, n equals 2, the next state, and so on and so forth. So de Broglie then inserted his wavelength hypothesis to this, and this is the part that I really love. If you imagine a one-dimensional wave, you imagine the orbits are like strings that are vibrating, and you take these standing waves on a string and then you wrap them around the orbit, you wrap them around the nucleus. He got basically an agreement between each of the standing waves one would expect from the de Broglie wavelength and the radii and energies. So, for instance, your n equals 6 standing wave. Remember, n equals 1 has 1 node, n equals 2 has 2 nodes, n equals 3 has 3 nodes for the classical standing wave on a string. This is nothing, crazy in terms of quantum mechanics or anything like that. This is just basic standing wave. Okay. So, for instance, if you had up to the n equals 6 level, and you took this and wrapped it around the circumference, okay, where the wavelength would represent 1/3 of the circumference, the half wavelength, each node would be equal to 1/6, you would get the standing waves agreeing with what Bohr had predicted. So obviously this told de Broglie that the electrons have quantized orbitals because the only types of waves that are allowed are standing waves. The electron has quantized orbitals because the only types of orbitals that are allowed correspond to these standing waves. So here would be one way to look at it. Here you see the innermost would be a little bit hard to represent. The n equals 1 is the innermost. The n equals 2, you can see here's an antinode, here's an antinode. Here's the n equals 3, antinode, antinode, antinode. And in de Broglie's model, you would just see these standing waves, oscillate back and forth just like waves on a string. Unfortunately, de Broglie's one-dimensional model wasn't completely correct. You actually need 3 dimensions to represent the electron functions, the electron waves around the atom, but this worked. This worked at least for a good approximation, and explain these principal quantum numbers and why they existed. Why? Well, the electrons, as we force them to smaller and smaller regions, where basically the electron is trapped in the electric potential well of the nucleus, okay? And because it's trapped in there, it's like a standing wave. It vibrates back and forth, and the only allowed standing waves are the ones that are going to fit within that boundary. Now, confirmation of the particle and wave nature, I should say the particle nature was well established, but the wave nature of the electron was done in an experiment by Davison and Germer. This was done in 1925. And it was somewhat serendipitous. They had a nickel target. They originally had was a polycrystalline target, meaning that's made of many basically is pretty much amorphous, I guess. But in any case, they were taking low energy electrons and they were bouncing them off these metal targets, and air got into the vacuum chamber because you can't have electrons traveling through, just basically air. Air got into the vacuum chamber and oxidized the crystal. So in order to get rid of the oxide layer, they put it in an oven, didn't realize that they actually annealed the sample, meaning that they created a large crystal on the surface that they were investigating with the electron beams. And what they saw when they did their experiment was there was a very strong reflection peak at around 54 volts, a very strong reflection peak at 50 degrees. And what was happening here is that essentially they were doing what is comparable to X-ray diffraction, okay, Bragg diffraction. They were doing X-ray diffraction off of the nickel crystal, and the nickel crystal would act like a diffraction grating. So this first order diffraction peak that you see right here would occur at 50 degrees, corresponding with the spacings of the nickel crystal planes. And by the way, this was done, another shout out for New Jersey. This was done at Bell Labs, and Davison shared the Nobel Prize with George Thomson in 1937. He had actually demonstrated, a similar effect, but a diffraction effect of electrons through thin metal. So these were very, very important in establishing that, in fact, de Broglie's hypothesis was correct, that these particles with mass actually do have a wave nature to them. It's just a very small wave nature to them. I mean, the wavelength is very, very small, and thus it is detectable under only certain conditions where we can take advantage of that very small wavelength.